All right, so how do we solve this? This is a very interesting thing, and I think it points to all kind of important things that people find useful in physics. So here it is, the way maybe we can think about it. Think variational method. What is the variational method? You write a wave function, and you try to see what is the expectation value of the Hamiltonian on that wave function. You calculate it, and now you know that the ground state energy is below that number, because for the real ground state, the expectation value of the Hamiltonian is the ground state energy. For an arbitrary state, it's more than that. So the variational method says, okay, if you want to figure out what is a good wave function, compute the expectation value of your wave function in the Hamiltonian, and then you will see, you will get some energy. If you tinker with your wave function, you can get to the right energy. So this is what we're going to do. We're going to try to take this psi of RR and put the total Hamiltonian here. And now the psi of RR is going to be this one from now on. This is the psi of RR. We'll put it here. And then I'll put another psi of RR. And I have to compute that. But think of it. It's actually pretty nice, the situation. It's computing this, you could say, how can I compute that if I don't know the etas, the eta, the single eta that is there? I know the Hamiltonian, but I don't know the eta, so I can't compute this. But think of this, really, this is an integral, because it's an inner product over all the capital R's, an integral over the little r's, and you can say, oh, I know the little r's here. I know them very well. I found them. I found this phi r. I've determined it. Some way you did. So if I know that, I know the little r dependence, and I can do all the little r integrals. If I can do all the little r integrals, means that, you know, this wave function is a product, this wave function is a product. This I can reduce to the following: eta of r, because this one I don't know, and an eta of r. And I claim that all the part that had to do with the phi of r, we can take care. And then there's going to be some Hamiltonian here left. And this we're going to call H effective of the r degrees of freedom. So a lot of physics in that step. Seemed like we did nothing. But look, I'm supposed to minimize this by adjusting my trial wave functions. OK, but I don't have room to adjust the phi because I determined it. It's a good one. So I put it in, and I calculate this. Now I have to minimize this. But if I have to minimize this for just the nuclear wave function, I have found the effective Hamiltonian for the nuclei, in which the electron has essentially disappeared from this interaction. It just doesn't play a role anymore. This is the idea of effective Hamiltonians for slow degrees of freedom when you integrate fast degrees of freedom. The fast degrees of freedom are your electrons. We're getting rid of them. We're integrating them. We're going to try to do that. So this will be an effective Hamiltonian for the nuclear degrees of freedom. So let me do one term in here. One term, you can play trying to do other terms, and well, the notes will deal with that. So let's consider the term HE. This Hamiltonian is some terms plus HE. It's over there. So let's calculate what HE does. So I now have to put effect of HE. So I have to put here eta of r. So let me put the whole thing. It's integral over all the r's, the r1, r2, r3. Integral over all the little r's. That's an overlap. Eta star of all the r's, that's the bra. Phi star r of little r. HE, then etas of capital R, phi r of little r. Everybody happy? That's my term. That's the contribution of HE to the left-hand side. Good. Now, HE is an operator and looks at this thing and says, well, I don't take derivatives with respect to capital R, so I'm there. I take derivatives with respect to little r. I have a multiplicative factor, another multiplicative factor, so I basically act just directly on this. But HE already acting on that gives you the electronic energy. So this would be the electronic energy in the ground state. That depends on R times phi r. And lots of vectors. Okay. So this integral now becomes integral dr eta star of r. Then I'll put the other integral d little r, phi of r star of r. And then I have just this number times eta of r. All right, so what is this integral? Happily, this is just a number. It goes out, and this is an orthonormal state. So this whole thing is dr eta star of r, E of r, eta of r, which you could say is eta of r, the number E of r, times eta of r. And therefore, you've confirmed that the contribution to the effective Hamiltonian of all this electron cloud is just this number, the electronic energy, like that. So in the effective Hamiltonian, H effective, there will be some terms, and there will be E of r. That's one term. Okay, so what is the whole answer for the effective Hamiltonian? No way to guess it, I think, unless you're, wow, you have an incredible intuition. It's going to be a little complicated if you think about it. Why? Suppose this term is going to create no trouble whatsoever. It's just going to copy itself. This thing doesn't act on the electronic wave function, so the electronic wave function is going to cancel. It's just going to contribute by itself. So this term we've done. This term is easy. It just gives itself. But this term is tough, because this term takes derivatives with respect to capital R, and your wave function depends on capital R. So it's going to be interesting. So what is the answer? I want to give you the answer rather than do that calculation. And it's almost like sometimes physics seems to have just a limited bag of tricks. Things come out in some way or another in a simple way. So what is the effective Hamiltonian? You could say, OK, it's going to be the sum of kinetic terms, 2m alpha over alpha. And you have p alpha squared. Well, it's not going to be just p alpha squared. It's going to be a little more. And then there's going to be a potential, a great potential of R. And that great potential of R is going to include the nuclear R potential. We said that this nuclear term would just copy along. The HE we calculated, and that gives us the EE of R. And you say, well, maybe that's it. But no, it's not that. That's it. So let's see what it gives you. OK, so here it comes. You remember electromagnetism? You could change this thing here. Well, it gets changed. And it will become P minus A alpha. Like if there would be a connection. Like if there would be an electromagnetic field. There's no electromagnetic field here, nothing whatsoever. But there's one thing. And what is it? As we'll write here, it turns out to be a Berry connection. Because you have the adiabatic thing, and you have your states that depend on R. The Berry connection shows up. So it shows up like this here. And here it shows up in a couple of funny terms. A term of the form alpha h squared over 2m alpha integral dr gradient sub r alpha of phi r squared minus sum over alpha a alpha squared over 2m alpha. So that's the whole thing, but I haven't defined the A. What is the A? Well, it's sort of a Berry connection. So you know what a Berry connection is. It's a D with the R in configuration space of a wave function with the star wave function integrated. That was kind of a Berry connection. So it turns out to be very similar here. The A alpha vector of R is IH bar, the integral over the little space, the electron space, that's where you integrate things, of the electron wave function star times the gradient with respect to R alpha of the electron wave function of R. That is the Berry connection, if you remember. It's an overlap of a wave function, and a gradient with respect to the configuration space. So that's a good Hamiltonian for a molecule in the adiabatic approximation. If this looks complicated, this is already much simpler than what the real problem is because of the adiabatic approximation. If you have these wave functions, these electronic wave functions, you can calculate these A's, and this plays the role of the effective Hamiltonian for the nuclei in this approximation. So the variational principle essentially told us what is the right way to describe the interactions of the nuclei given that the electrons have already been fixed into a class of wave functions. Now, in general, this is the complete solution, but in general, it's hard to do it, still complicated. So many times people simplify. Well, it might happen, for example, if you have a simple enough molecule that your wave functions phi r are real. Now, you remember that the Berry phase vanishes when the wave functions are real. These things have to be imaginary with another I. They have to be real. Connections are always real. Real operators in a sense of R. So if the electronic wave functions are real, forget it. There's no Berry connection. So many times the Berry connections are not there. Even if there are no Berry connections, this term might be there. This is the gradient of this wave function with respect to the capital R. And this term can be important even if there's no Berry connection. So in some cases, the lowest order approximation of this, I think that's what is classically called the Born-Oppenheimer. Ignores the Berry phase and ignores this extra term. So in that approximation, the lowest order approximation, the effective Hamiltonian is just the sum over alpha minus h squared over 2m alpha Laplacian R alpha plus the nuclear potential plus the electronic contribution to the potential. So you keep basically, forget about Berry, that's higher order approximation, higher order approximation, higher order approximation, keep just the P, keep the nuclear, keep the electronic. And people have done a lot with this. So that's our treatment of molecules. A pretty interesting thing, and perhaps the most important lesson of all of this is your way in which you can see how light degrees of freedom impose dynamics in slow degrees of freedom. And that's something you do in physics, in quantum field theory all the time. You have the slow-moving degrees of freedom and the fast-moving degrees of freedom. And you integrate the fast-moving degrees of freedom, and you find an effective Hamiltonian for the big things. You may have quarks and all kinds of complicated things, but at the end of the day, they form protons and neutrons, and you can integrate the interactions of the quarks to sort of find the dynamics of the particles that you observe. So that step in that top blackboard is pretty important.